For the second half of Chapter 9, we're going to look at all three of our shapes now in polar form. So Chapter 8, we took some time, we did rectangular coordinates, we did the exact same thing in polar. So Chapter 9, the first half, we did rectangular coordinates for our three conics. Second half, we're going to look at polar equations for these. So it just requires us to think a little bit differently about these, different graphing system, but the shapes are going to be the same. Okay, so make sure you have some good notes here and you have those steps so we can work through those in class. Okay, by definition, we looked at how we created these three conics using foci, points, and directrix. Directrixes. So parabola is the only one that we actually graphed a directrix with, but ellipses and hyperbolas have them. We don't put them in there. They're just on the other side of the foci. Okay, so we're going to define this thing called eccentricity. So we're going to say distance from F, which is a focus, comma P, so distance from focus to some point on the conic, and we're going to look at it as a ratio of distance D, directrix, to that point, and we're going to define that as eccentricity. So think about how we created each conic and how it applies to eccentricity. So if distance from foci to the point is greater than, less than, equal to, as distance directrix to point, then eccentricity would be 1, greater than 1, or less than 1. Okay, it's kind of what we're looking at here. Here's how we define these things. If the eccentricity is 1, the conic's a parabola. That just makes sense. Distance focus to point is same directrix to point. By definition, that's how we did a parabola. So you don't need to remember that one. If the eccentricity is less than 1, not necessarily negative, just a fraction, the conic is an ellipse. And if the eccentricity is greater than 1, the conic is a hyperbola. So those are the two you're going to have to keep straight here. We define eccentricity as C divided by A. So C is always the distance to the focus, and A is always distance to your vertex. So one way you can think about it is with this simple equation here. If you have an ellipse, your foci is inside your vertex. So therefore, this distance here is C. This distance all the way out here is an A. That means the C is smaller than A, which means you have a fraction, which means you make an ellipse. You have a hyperbola. Here's your vertex. Here's your center. We call that distance A. If this is your foci for a hyperbola, that distance coming all the way out there is C. Therefore, C is the longer distance, which makes it bigger than 1. So you have a hyperbola. Another way to look at it is with the Sketchpad file. So a conic section can be defined as the locus of all points R in a plane such that the ratio of the distance from R to a fixed point to the distance from R to a fixed line is a positive constant E. Okay, so they changed up the variables a little bit here. So right now we have an ellipse. You can see the distance RF is less than RH. Okay. We can reset this guy to a parabola, the one that we know for sure. So this distance is the same as this distance by definition. So as we start moving E around, so now that ratio is 1.5. So the distance from R to F is greater than R to H. So you're moving further and further away from this fixed point, and it's getting closer and closer to this directrix or that fixed line there. Okay, ratio gets even greater. So that distance is really huge, that distance is small. So if it's bigger than 1, it's a hyperbola. So you can see this moving along the point here. So now we have an ellipse. We can swing this guy around here, so that distance is smaller than 1. So it's a larger distance from the point to the directrix as it is from the point into the foci here. And you can see that ratio there. So as soon as it gets bigger than 1, it becomes a hyperbola. If it hits 1, it becomes a parabola. So now that we know what eccentricity is and how it's going to define the shapes, we want to start looking at how we're actually going to graph these things. We're going to get the same picture that we used in Chapter 8 to get all the connections between rectangular and polar. So this simple guy here, we're going to put a foci or focus right at the pole. You also have a directrix back here. All the shapes in this case are going to have them. Sometimes we can graph them, sometimes we can get away with them. So first half of the chapter, we looked at graphing something like -5, 0. Now we're going to graph 5, pi. So in the direction of pi, come out 5 units. Here's the equation we're going to use. Now, how they get this is starting with this guy right here, and they take this piece and they multiply it up here. They do some substitutions, a bunch of stuff happens. You can look at the proof there in your book, but basically you end up with this. Now there's a couple things that are going to change with this. This case is a polar equation with a conic with a cosine. Sometimes they'll have sines. Now, so radius equals e times p over 1 plus or minus, that'll change, e, which is our eccentricity, cosine theta. So for these, the focus is always at the pole. The directrix is a distance p from the pole. That's this guy right up here. E is always the eccentricity. Now, if it's a cosine, that means your directrix is always going to be perpendicular to the cosine axis, which is the x-axis. So if you see 1 plus e cosine, your directrix will be perpendicular to the cosine in the positive direction. If you see 1 minus e cosine, your directrix will be perpendicular back this way. So if it's a cosine, it's perpendicular to that axis. If it's plus, it goes plus. If it's minus, it goes minus. Here's your equation with the sine. So same thing again, except it's now eccentricity times sine. Your focus is still at the pole. Your directrix is still a distance p from the pole, so whatever we'll solve for the p values, e is still eccentricity. Now if it's a sine, it's perpendicular to the sine axis, or y. So if you see 1 plus e sine, it looks like that. If you see 1 minus e sine, it looks like that. Okay, that's where your directrix is. Here's the 6 steps. If you have these and you follow through them, you will be able to do these. Okay, you're not going to get them right away, but after a few days, they will make more sense with more and more practice. Here's the 6 steps. Make sure they end up in your notes. First thing we want to do, solve the equation so it's 1 plus or minus whatever is on the bottom. Now there's going to be numbers all over the place. This is the guy you want to turn to a 1. Okay, you don't want to turn other things to a 1. Okay, we need that guy to be a 1. Find eccentricity and find p. You'll grab eccentricity right off of here. You can solve for p off of this. Determine which axis it's on. So is it a cosine or is it a sine? If it's a cosine, your directrix is going to be like this or this. If it's a sine, your directrix is going to be like this or this. Determine the shape. So what's the eccentricity? Okay, if it's 1, if it's a parabola. If it's less than 1, we're going to say it's an ellipse. If it's greater than 1, it's a hyperbola, and that comes from this ratio and also your Sketchpad file. We're going to plug in 0, pi, pi over 2, and 3 pi over 2. Those are super easy values with both sines and cosines. 1, 0, -1 are the only things that are going to happen. Those will give us 4 points, and then we're going to graph them. So in part 2, we'll try and do a couple examples here.